still want to see me, or you are happy?
I'm eager to see you.
Because now we are going live from Chicago, and it's Tuesday morning, and life is beautiful outside, but here we are stuck inside. Sorry. Question. Andrew, you had a question?
Yeah, it's not about lecture. It's actually kind of related to the homework.
Yes.
Yeah, I think maybe Bar was asking about this, but I'm just a little bit confused about the extended complex plane. Don't know how it works, really.
Yeah, so none of you asked me to give you a lecture on Riemann sphere, so I'm a lucky guy, I don't have to do it, but I was willing to do it for the cause. So the extended complex plane is when you look at very large values of z, you wonder what's happening there. Very, very large values. Now, a useful operation in changes of coordinates in complex analysis is if you change coordinates from having function z to function, w equals 1 over z. What does that function do when you change the coordinates? It doesn't change anything on the unit circle, because on the unit circle, inverse of the function, just sends the phase into minus phase. That's easy enough to visualize. But what it does is it sends infinity in original problem to the origin in the variable 1 over z. Now, origin is no big deal. You know how to work around, everything that's smooth is smooth around the origin. So what Riemann realized is that the entire circle at infinity actually corresponds to a single point, because if I change the variables, it becomes a single point. And that's called, Riemann sphere. So in a complex world, you just wrap up infinity and crunch it in a point, and then you show that that point is not very special because I can translate coordinates, etc. So actually, the complex plane is a sphere, Riemann sphere, where things that are circles map through the origin into circles. Things that they used to be a line, once you reflect them through the unit circle, so they go from plus to minus infinity. In your original picture, once you write them in 1 over z variable, they become little circles. So lines are just special circles that happen to go through the point at infinity on a Riemann sphere. Everybody else is on a circles. And that's what that exercise was about. That's that complex plane.
Okay, so I guess we were sort of intuiting from the question that it seemed like the two lines that we draw at a certain slope, it's the distance d from the origin that is related to the fact that when you send your circle to infinity, you're gonna turn into lines. And
yeah. So think of this as living on a planet Earth and being representative of a major party in the United States, which knows that Earth is flat. And this is correct, right? Because as I stand here, a line that I draw goes from minus to plus infinity. And what's the problem? Actually, if I draw a line either on Earth on Riemann sphere, that line goes around on a great circle and comes back and eats my tail. So every line that I believe a flat earther or a representative of a major American party is a circle. And so all straight lines are just special cases of circles on Riemann sphere.
Okay. And then I guess the last part of my question is...
And also that exercise, and I added a little footnote in the notes itself, I rotates by 90 degrees. That's the big trick. So whenever you're going someplace, if you multiply by I, you go that way. And if you were on a radius of a circle, get to the edge of the circle, then the tangent on the circle is just multiplication by I, because its tangent is always at 90 degrees when you get to the edge of the circle. So that, I think, was that problem. Go ahead.
Yeah, so if you are starting with a circle that's displaced by d, and then you send it to infinity, then you get these lines that are d away from the origin. But
Yeah.
why is it not the set of all lines that are distance d from the origin? Why is it just the two lines with that slope? Is it because the direction you send it to infinity that matters?
Yeah, it matters. Yeah, because, again, we are flat earthers. So I stand here and I'm armed and I shoot you and I shoot the next person. It's my right to do this. I do this at different angles. Now, my bullet is a very good bullet. It goes around the earth, comes and hits me in my back. But the angle matters. They're distinct lines because I'm doing it at distinct angles.
Okay. But if you're at infinity, then there's no.
Well, that's what you think. But that's a brilliant Riemann realization. That actually in complex plane, infinity is just point like all other points. And you see this by inversion through 1 over z, inversion on a unit circle. And then you realize that, on a complex plane, there are two things you can do. You can translate. So for example, I can have a point at the origin, but I can, in new coordinates, I can add, 1 or I to it. And then it moves. That point is no more at the origin, but it sits at 1 because I translate it by just adding a complex number. So I have a translation. So, and then you worry, what does it do to the point infinity when I translate? But then I have the operation of inversion. So, I can invert the coordinates. So point at infinity gets mapped into my origin, whatever my coordinates are right now. Then I can translate that point and I can send it back because inverting twice is, inversion of inversion is identity. So there's nothing special about infinity, just point like any other point. And I can reach it by, taking steps, infinitely many steps, or I can, it's totally democratic. And, that was a beautiful Riemann realization. Complex planes is so magical. It's actually a sphere.
Okay, so I just want to make sure it's not a property of the limit, right? It's a property of the point at infinity.
No, it's a property of complex plane. And, it's totally non-obvious because mentally we start with a flat object that seems to run from plus to minus infinity. So when we work in a real calculus, minus infinity is totally different from plus infinity. There's no relation. Magic of a complex plane is that if you replace function of x by function of z, then infinity in magnitude of z, an angle which has a feeling, this actually is a point, so the whole thing is sewn together and no point is special. What you think is infinity right now, after I translate it, that infinity changes. Every point on the sphere, just like every point on planet Earth, if I'm not measuring accelerations, rotations of a planet, is equivalent. They're all the same. So that's amazing thing.
Okay.
And we will use it, with these contours, it means, I can move the contour over infinity. It doesn't matter because infinity is just a point like any other point on the sphere. So basically, it works like this. Imagine you're on some kind of sphere, and you take a circle on that sphere, so you're on a sphere and the little circle is locally just a circle. Very close to you, it looks like it's a circle in a plane because very close to you, the world looks flat. So now you make that circle bigger and bigger. And at some point, that circle goes, if you're on the North Pole, that circle actually goes to the South Pole. That's called the Great Circle. And that one on your plane looks like it's going off to infinity and coming back from infinity at that particular angle where you're shooting to the North Pole from the South Pole. Now, if you miss the South Pole by overshooting a little bit, then that'll be again a circle and, smaller and smaller circle as you come closer and closer. So you can imagine you take a sphere, you take a plane that goes through the North Pole, and as you change the angle of the intersection of the plane, there is one particular value at which plane goes through both poles, and to you that looks like infinite line.
Great circle.
And everybody else looks like a circle. So line is just a special non-generic representative of circles in complex analysis.
That's only true in complex analysis?
Yeah. And, it's never as good as the first time. It was amazing in 1810, 1840. It's a little bit like in quantum mechanics in 1920s. You were 22 years old, your frontal cortex hasn't developed yet, but you could do amazing mathematics or amazing quantum mechanics. And then from then on, it's been hard work because it turns out they try immediately to generalize from complex numbers to quaternions. And, beautiful things happen with quaternions. Engineers use them to do rotations, etc. And we will learn some of the stuff. So, there's still some magic, but there is no complex analysis quaternions. There are none of these beautiful theorems about integrations if you're in 4 dimensions, as quaternions are. Then you can go to octonions, and then it's really tough. It's very special. You end up with something called exceptional groups and monster group in finite groups, and the string theory and all kinds of crazy stuff. No relation to anything that we are aware of. So, mathematics can be generalized and gets richer and richer, but it's never as good as the first time. This time was amazing. And, it's so powerful that we use it in our daily work today, because we do have to compute lots of integrals if we are theorists, at least, especially if you're doing quantum theory, statistical mechanics, or biophysics.
So quaternions are just a generalization of the real complex plane into 4 dimensions, and vice versa, octonions into 8 dimensions?
Yeah, but, the trick about what made this complex analysis special was that there was a matrix. It's all based on matrix, 2 by 2 matrix, which is 0, 1, minus 1, 0. That's called I. That's the rotation by 90 degrees in 2 plane. That has a magic property that if you do it twice, you get minus 1. You get, half of a turn. Now, one generalizes that. That's called unitary group of in 1 dimension, complex numbers, or special orthogonal group in 2 dimensions, rotations in a plane. Now, it can be generalized to SU2 complex numbers, pairs of complex numbers, or SO3 rotation in our space. That's called quaternions. And that kind of works, but you don't have this beautiful complex analysis that comes. There are no equivalents of quantum integrals that I'm aware of in 4 dimensions. But it's useful in designing computer games or designing, astrophysical things. Sending spaceships various places. It's a quick way of computing rotations. Octonions is the end of the road for this way of thinking. you can generalize it to where the units are still square, 8 of them, octonions, there are 3 imaginary units, their square is -1. Now there's 7 imaginary units whose square is -1. But then a thing that happens that you're really, really not ready for when you use only 2 matrices, the multiplication is not associative anymore. That is to say, if I multiply 3 numbers, first these 2 matrices times third, or this one times the product of them, you get different results. And that's really hard to comprehend. It's mathematics, so you can check it, but it's not very intuitive. And then a great mathematician who happened to be a woman, Buffon, described the geometry of that space that's called Buffon planes, etc. But it's all hard going, and you get tenure for doing anything on this. And there are lots of people who spend their life studying things associated with octonions. And I can report as a physicist that I'm not aware of any measurement in physics that measures an octonion. And even quaternion, you can always just think of them as pairs of complex numbers, so they're not special. They're So, all the attempts to write quantum mechanics, not in complex plane, but in quaternion or octonion plane, they either were not fruitful, meaning, you just rewrote what you already know in some other notation, or they failed in terms of octonions. They just fail as far as I'm aware. So this road doesn't continue, but what does continue is what I'll teach you. Notions about symmetry continue being very powerful. So that's how modern theoretical physics and mathematics have developed since.
So I was able to understand the first case when you have this kind of equation and you want to find the roots of A and B. But I could
so I sketched it in a lecture. I did it very quickly and messily, but it is in a lecture from last week, second lecture.
I just want to understand the fact when B is 0. Intuitively, what's happening?
When B is 0, it probably mean that discriminant, the famous combination of trace minus 4 times determinant square root of plus minus. That's probably 0, which means that the 2 roots probably don't differ. It's a real root twice instead of having 2 distinct roots, I'm guessing.
Yeah, that seems right. Okay, thank you.
So it's a special case, which is important. So there's something in, theory of stability, which is called bifurcation. So if you have a differential equation and you change some parameter, and it happens to be a 2-dimensional differential equation, so you are computing its stability, 2-dimensional Jacobian. There is a quadratic equation, and the roots could be real distinct pairs, which means that the differential equation attracts in all directions or repels in all directions. But then there's a special case when the roots get together and become one double root. And as you move through that point, you can go into complex planes. So the things that used to be overdamped oscillators suddenly start oscillating. And the technical term is a bifurcation. 2 branches have happened at that point. So it's an important point. It's a special point, but the qualitative behavior of the system changes at that point. And you go from things being hyperbolas to things being sines and cosines. So it's very important, special point.
Okay, thank you.
Anything else? Ulrich, you okay? Thank you for coming this week. It's my pleasure to see you.
Glad I could make
All
it
right,
this
guys.
time.
Yeah, no, but it's, there are more important things in this course, and this is online anyhow, if you. Now, what I find is that I never go and watch recordings online of things. The live presentations I do, but so I don't know how you do it. But anyway, bye.
See ya.